So I am Paul Nation. I'm from IBM, and I'm here to talk to you about our software stack. Okay, so our software stack is in general called Qiskit. I will start with a caveat. Everything I'm going to talk about is not released yet. Okay, it's that new, it doesn't come out for a week and a half. Okay, so kind of to wet your whistle. All right, but let's go back and take a brief pause and see why we're here. All right, so in the last 10 years, we've seen a transition from quantum systems that are in the lab of universities around the world, 1, 2, 4 qubits, okay? And we've reached what's called, or what we call this quantum-ready regime, okay, where you start to have devices that are large enough to actually do practical applications. Okay, and then at some point, of course, we would like to be in this quantum advantage where we are actually driving benefit from our quantum devices. Okay, and this quantum-ready quantum advantage is usually stated in terms of qubit count. Okay, so today, we're on the order of around 10 qubits. Okay, tomorrow will be 50 to 100. Companies have announced somewhere in between there. And of course, somewhere in the future, we'd like to be fully fault tolerant and have millions and millions of qubits. Okay. So at IBM, we have been working on this for some time now. Okay, so for the last 2.5 years or so, we've had 8 quantum devices online. If you look online, today, these are the 3 you would have. We have a 20-qubit device called Tokyo. This is available to people on the IBM network. And we have 2 smaller devices. One is 14 qubits and the other is 5. Okay. Also, I'll point out that this is a Jupyter Notebook interactive widget that you'll be able to use in a week and a half. Okay, so this is what you can run today. We're kind of proud of our devices and our setup. Okay, first of all, everything is fully internet accessible. You do not have to email us CASM code, right? You just log in and run it, right? Our devices are stable. Okay, our devices are up 24 hours a day. They are down once a day for calibration at set time, and they're back up again running jobs. Okay, we also do not hide anything from you for our hardware. All right, again, what you're seeing here are clips from a Jupyter Notebook that you can actually run. This is our Tokyo device. We tell you everything about the device. You can see in the bottom there, that is an error map. It's a color-coded map that tells you all the errors about the device. You can see all the jobs that you ran on the devices. These are available to all. Everyone in here can actually go, log in, get an account, and run on our hardware today. And what's not talked about so much is that actually we have the ability to take third-party devices or maybe an online quantum simulator and actually integrate them into our system. So if you don't want to go through all the trouble of having a queuing system and whatnot, we can actually take care of that for you. Okay. So we've had some success with this. So this is stats for our public users. So we've had 100,000 plus users. They've run over 6 million experiments. We've had 130 or so scientific papers on the topic, and so we're quite proud of that. We don't show the numbers for clients, but we could say we have quite a few people in our IBM Q network. You can see on the right there startups. I think most of the people here we actually collaborate with to some extent. We also have hubs, KO University, they're here in the audience, and also other partners as well. Okay. So now, usually when people talk about, quantum advantage, quantum supremacy, these are framed in terms of qubit count, okay? But this really does a disservice because it turns out that having a classical computing infrastructure is nearly as important as actually how many qubits you have, okay? These things really go hand in hand, okay? And so I think at least IBM, of course, Microsoft and Google have also probably known this for some time, that you need to develop a good software infrastructure for running a quantum computer, okay? And at IBM, we have one for about 2 years now, which is called Qiskit, the Quantum Information Science Kit. So this is an open source Python library that you can just start playing with immediately, okay? It just requires pip install, okay? And it has about 120,000 downloads to date, and we're proud of this as well. Okay, and recently we've kind of refactored our software into what are called elements. Okay, So these are the elements of Qiskit. Okay. The ground floor is what we call Terra. Okay, not surprising there. All right, Terra's entire job is to create circuits, or perhaps pulses, which I'll talk about at the end, optimize them, and then run them on our hardware. Okay, so that's the entry point to the hardware. Aer, which I'll also briefly mention, is an element for classical simulators, emulators, and debuggers. Okay, and I'll briefly mention this as well. Ignis is error characterization and mitigation. Won't talk about that much. That's the last one to be released. And then sitting on top of all of this is Aqua. Okay, and Aqua are algorithms and applications for near-term, i.e. noisy devices. Okay, so there's a lot to digest here. I'm only going to talk about Terra and then make a brief mention of Aer. Okay, so what's the workflow for our software? Well, it follows basically everyone else's software. First, you got to build a circuit of interest, maybe more than one circuit, right? If it's less than roughly 50 qubits, right, it's probably beneficial to simulate it. All right, so do so if you can. Third, okay, we're interested in running on actual quantum hardware, so you have to compile it for your device, okay? You execute it on device, and then you would post-process however you want, okay? I am really going to focus on the third, okay, because it's not talked about too much, but it's actually a very complicated problem and a very important one. So that's what I'll focus on. So let's make a simple circuit. So I've done this here, okay? You can see the Python code from Qiskit import star to make life easy, and you can build your quantum circuit. And I've drawn the circuit diagram at the bottom. Okay, so this is the circuit we want to play with. All right, so again, this is a 5 qubit circuit. 5 is less than 50, so let's go and simulate it. All right, well, I told you that Aer is our simulation module, so I'll briefly describe it because it's not released yet, so why not tell you something about it? So Aer is ultra-high performance classical simulators, simulators on GPU and CPU. Okay, in the upper right is a simulation on Intel processors of a quantum volume experiment. So this is a random circuit that's difficult. Okay, and as your qubit count grows, we're 50% faster than the competition. Okay. Aer has multiple simulation models. You can do Chasm simulation, you can do state vector simulation, unitary dynamics, Clifford, tensor networks, decision diagrams, which is actually a joint project with Jonas Kepler University. Okay. Configurable noise models. Okay, we don't talk about noise very much. We've had noise simulated for some time. It was just hidden. All right, but we've given you like the full capability to implement essentially all the main types of noise that one would be interested in. Okay, and this is also a starting point to have your own simulator integrated with Qiskit. So if you have your own simulator, maybe you think yours can beat ours, or you have a different design, it's actually easy to take Aer, reformat it into your own, and then your simulator will be available to everyone who uses Qiskit. Okay. I also mentioned GPU. Okay. The bottom right is a comparison with other simulators for GPU. Microsoft Q# doesn't use GPU, so that's a CPU one only. Okay, but if you have a lot of GPUs and a power 9, all right, you're 2 orders of magnitude better. Okay, this is something that will only be available for members of the IBM Q network. Okay, so that's a brief snippet about Aer, right? So let's actually use it to calculate what our circuit does. Right, so here's the code for doing that. The first line says from Aer, get a backend. Aer is something we call the provider. It provides backends. Simulators are actual hardware. That's what we call a provider. Here we're grabbing our Chasm simulator. We're executing it on that Chasm simulator. It does it asynchronously. You get a job. You can ask the job for the results. And here we find out that our circuit, with 100% probability, flips everything to the one state. Okay? So that is what happens if we do it on a unitary simulator. Okay? But if we go now to the real world, we know the real world is messy. Okay? That's not what's going to come out. Okay? So in the real world, you have a bit of noise. Okay? And so we want to understand how, with our noisy devices, this thing is going to behave. And it turns out the answer is not so simple, okay? Our devices are noisy, okay, and our devices have limited connectivity. Okay, so not every qubit talks to every other qubit. So we have to rewrite our circuits. We have to rewrite them to map to topology, okay, and you also want to make them as small as possible, right? Because if you go too long, you hit noise. Right? And it turns out there's no unique way to do this. There is an optimal answer to do this, okay, but there's obviously other answers. So here I have a bit more cleaned up version of our initial circuit. I want to map it onto our 5-qubit processor, okay, because it's a 5-qubit thing. There's a good way to do this, i.e. an optimal way, that's the green way, okay, and you see that our circuit remains the same length, okay, and then there's a bad way. There's infinitely many bad ways. I've just showed you one that happens to be twice as bad as the good, okay? And so when you compile, this has a dramatic effect on what the output is. So here I've actually run these on our 5-qubit device. Green is good, and red is the bad results. And again, the result on the far right is the one that is correct. And so you can see that the chance of getting the correct answer is basically double if you have the good circuit, and half as much if you have the bad circuit. Okay, so actually how you compile your circuits, rewrite them for your hardware, okay, makes a big difference. We know the answer in this case, but you can imagine running something on maybe a 50-qubit processor where you don't a priori know the answer, right? If your circuit is too long, you just get jumped. You can't pull your answer out of noise. So this is a big deal to actually run on noisy devices. So we have a way of handling this in our software, okay? And this is what we call a transpiler. So a transpiler is just a set of passes that take your initial input circuit, and each pass does something very basic to it to transform it into, hopefully, the optimal final output. So in our software, we have a generic set of passes that require no user intervention. The first one is unroll to basis, which basically means you can give me almost any gate that you want, but our hardware actually doesn't understand that. It has to be decomposed into elementary gates that we understand. That's unrolling to basis. Gate cancellation, right? A lot of the gates that get put in maybe can cancel each other, maybe can be simplified, and so that needs to be handled. There's a topology mapper, which also is called a swap mapper, okay, which makes qubits that interact via C0, nearest neighbor in the topology. And then maybe after doing that, you do a second round of gate cancellation, because maybe you can cancel some of the C0s, okay? All the passes are managed by what's called a pass manager, okay? And the pass manager is in charge of scheduling, and it also has global properties, right? So things like the depth of the circuit, the layout, commuting sets, fixed points, or fixed point conditions, all of these things are things of interest that actually will go and help you optimize your circuit. Okay? So we have a default set that is in general pretty good, okay? But we also allow users to modify the pass manager, input and remove passes. And so let's take an example of that. So here on the top, I have another circuit, okay? And actually using our pass manager, we can find out what it does. So that's the initial circuit at the top. On the left, what we're going to do is we're going to add to a pass manager a pass that says just remove redundant CX gates, C0 gates. Okay, so you build a pass manager, you add your CX cancellation pass, and then you call this and you say transpile. And what it did is it removed the two C0s that occur after each other between qubits 0 and 1 because they were redundant. You can cancel this. All right? And that's what a pass does. A very simple thing. I found two C0s that are redundant, and I removed them. All right? But we can go beyond that. We can now get a little more sophisticated and say, you know what? I want you to analyze the circuit and do a CX cancellation, but I want to redo it repeatedly until the depth of my circuit reaches a fixed point. Okay? And that's what we're doing on the right-hand side here. So again, I build a pass manager, and I'm going to add a pass that says analyze and cancel, and so on, okay, until your circuit has reached a constant depth. Okay, and again, I can do that and then what you get is you get the circuit at the bottom. All my CX gates have been removed. Okay, so I'm left with nothing but Hadamard gates one after another. If after this I said pass manager, cancel redundant single qubit gates, you would find out that this circuit does absolutely nothing. Okay, it's just the identity circuit. Okay, so we have a mechanism by which you can richly construct these passes, okay, and play around with manipulating your circuit before you pass it to the hardware. Okay, how it does this is it works on an internal data structure, which is called a directed acyclic graph, a DAG circuit is what we call it. Okay, and here I have a circuit, just a mix of stuff. It has a controlled NOT gate, for example. And internally, the graph structure on the right there is internally what it's labeled as. So each of the green dots are essentially the entry points. The blue circles there are all the gates and also the measurement operators, and the red are just the terminal points of the circuit. Okay? So the pass manager goes and it looks through this directed graph structure and actually computes what's going on with your circuit. Okay? Now there's two different kinds of passes. Okay? There's an analysis pass, which just reads your graph structure and then sets the global properties. And the next one is a transformation pass, which rewrites your directed graph structure, okay, reading those properties that you probably just modified. Okay? So the usual workflow is analysis, transform, and so on, but it can actually be dynamic. Okay? So given the result of an analysis pass, I can actually branch. If some condition is met, do path A. If not, do branch B. Okay, so it can actually become quite sophisticated. All right, so let's take a look at this. All right. So here is an example analysis pass. This one is a bit more complicated. So this is what's called a 2-qubit block collection. Okay, so here I have a circuit again at the top. What this pass does is it tries to group pairs of qubits by the operations that are between them. So in the blue case, qubit 0 and qubit 1, they have 4 C-naughts between each other, okay, a collection of single qubit gates, okay, but they don't talk with any other qubit, okay, so that's a 2-qubit block. The orange section is also a 2-qubit block because qubits 0 and 2 only interact amongst themselves later on in the circuit, of course. Okay, and again, on the right-hand side, you can see the directed graph structure and how those blocks are oriented in that graph structure. Okay. So that is the analysis path, but then what happens afterward depends on the result of that. Okay. So, for example, if each of those blocks has less than or equal to 3 C-naught gates, maybe my next step would be, well, why don't you map to hardware? All right, that could be an option. All right, but in this case, okay, the blue block has 4 C-naughts. Okay, the orange block has a swap gate. That's the vertical line with the X's on it. Okay, and a C-naught and a controlled unitary operation. Okay, the swap is essentially 3 C-naughts. Okay, and it turns out that if I have more than 3 C-naughts in one of these blocks, then what I'm going to do is I'm going to group them. Okay, I'm going to compute what the unitary is. It's a 4x4 matrix. It's trivial to compute. Okay, and then I'm going to run it through what's called a KAK transformation, KAK decomposition. Okay, and the reason I do that is because it turns out that any unitary that operates on 2 qubits can, in the worst case, be modeled by 3 C-naughts in a handful of single qubit gates, okay, in the worst case. So if I have here, again, like the blue block, it has 4 C-naughts, I can actually get rid of them, one of them, okay, by grouping them, computing the unitary, and then decomposing, okay. And that one actually has quite a bit of benefit. Okay. Okay. So that was an analysis, and then what I talked about later was a transformation, but I'll give you another example of a transformation path. Okay. This is what's called a local ordering path. Okay. So again, our devices have limited connectivity. Okay. So that constrains what you can do and makes mapping to the topology a bit harder. All right. what happens if I try to optimize my circuit for limited qubit connectivity? Okay? So this pass here does that. Essentially what it does is it looks at an input circuit. Here I have a 10 qubit example circuit that's essentially a Simon's algorithm circuit from one of our tutorials. And then I build a sparse matrix structure where the non-zero elements of the sparse matrix just tell me which qubits interact with each other via C-naughts. So for example, this matrix on the left here, qubit 0 interacts with qubit 5 a single time. Qubit 1 interacts with qubit 6, in this case twice, interacts with qubit 7 and qubit 8 as well. Okay? And you can see that these non-zeros are spaced a bit wide in the sparse matrix, so they're very far from the diagonal. Okay? So basically what this pass does is it takes this sparse matrix, okay, and it does a weighted graph traversal that tries to squeeze all the non-zero elements as close to the diagonal as possible. Okay? You can say this another way, okay? We are optimizing my input circuit for linear nearest neighbor topology, okay? And this is done using a trick from sparse LU decomposition. The circuit on the right is what I get after doing this decomposition, okay? It's the exact same circuit. I didn't change any gates. I just relabeled my qubits, okay? And then the sparse structure on the right is what I get by trying to squeeze it as best as possible, okay? So if you look at the circuit on the left and the circuit on the right, okay, they don't look like they would have much difference, okay? But if I go to compile one of these on a device, such as one of our ladder devices, which are called Melbourne and the now retired IBM Qiskit device, okay, then the circuit on the right is about 42% shorter than the one on the left, okay? And I did absolutely nothing but relabel qubits, okay? And we do have examples of circuits that have much wider structure in terms of their sparse matrix representation, that when I do this trick, I can reduce the depth of the circuit by an order of magnitude, okay? And an order of magnitude depth can obviously mean the difference between having a circuit that gives you junk because you've hit your noise limit or actually gives you a real result, okay? So these are the kind of things that we've been working on, okay, to try to deal with the fact that we do have noisy devices, okay, but we can be a bit smart about how we classically manipulate the input circuits, okay, before sending them off to the hardware, okay? And there's a lot of work to be done. All right, this is just the beginning step, and again, this will be available in about a week and a half, okay? So that's all I want to say about that. What I want to talk about in the last real slide here, I realize I'm going fast, is something called open pulse, okay? So up until now, on our hardware, what you would do is you would specify a circuit, and then you would send that circuit to our backend. Internally, what that does is it gets sent, every gate gets turned into some pulse that gets run on the qubit, okay? What we've decided to do is open our hardware up where initially, at least, members of our IBM Q network can start to manipulate our hardware at the pulse level, okay? And then here's an archive link which talks about this specification. So essentially what this means is we will start to allow you to directly manipulate the actual Hamiltonian of our device. So here I have a Hamiltonian for a 2-qubit version of our devices. Okay, I've underlined a couple of the terms in that Hamiltonian. These are time-dependent terms. These are the terms you can actually manipulate directly using our open pulse format, okay? So why do we do this? Well, at IBM, we're interested in actually fundamental physics, and so we are interested in manipulating our Hamiltonians at a bit lower level, but we're also interested in opening this up to other people because it allows you to do a variety of things. First, it allows you to do optimal control, right? If you don't like our gates, you can optimally control and do better, right? Dynamical decoupling, you can start to do noise mitigation using open pulse. Hamiltonian tomography, You can actually probe the Hamiltonian structure, find terms that are there that you don't want to be there, go back and change your pulse shapes and get rid of them. Okay, so it's very good at trying to kill noise. Okay. And included in this is also our Markovian noise simulator, so you could actually simulate our devices on a classical system up to, let's say, 20 qubits. Okay. So we're very excited about this. This will come out shortly as well. Okay, so we're going beyond the standard circuit model and really starting to probe our hardware at a deeper level. Okay. So I think I have plenty of time for questions. All right, so I'll just leave it there. Thank you. Okay, I can't see anything, so it's pretty bright.
Oh, I'm just going to shout mine out.
Okay, well, I can see you, but yeah.
So it's not too often that hardware vendors let us control hardware. Are you sure we won't break it?
Well, there'll probably be some limitations in there.
But that's pretty new, isn't it, to allow people to...
Yeah, no one else does this, right? So, I mean, so what will eventually happen is you can query a select number of devices. Not everyone will have this, but you can query some devices, and they will return essentially all the pulses that are configured for them. So you could use those at a starting point, or for example, you want to do a controlled NOT gate that you've optimized via grape, crab, goat, whatever animal or fruit you decide, and then you can actually try to run it, and you can see what happens, right? So it's actually a pretty cool thing. Yeah. All right.
When you make a measurement with your measurement gate, how do you control the axis to make the measurement? Question number one. Second, on these pulses, can you have a lookup table to synthesize some waveforms for those pulses?
So we have a fixed measurement. We're measuring in the Z basis all the time. We don't change the orientation of the measurements, at least not on our available devices. Is there so for the pulses, there is in some sense a lookup table. We call it a default pulse library. And so essentially there will be a pulse that's called, X90, for example, which will be the pulse that's done for doing an X90 gate. And then these are the pulses that would actually be implemented and are returned by calibration. But these would be starting points, for example. I mean, pulse is not very interesting if you don't actually try to make your own pulses, right? So we provide a default pulse library, but again, the expectation is you would probably want to go in there and start playing around with pulse shapes. Yeah. Oh, yeah.
On the dynamical decoupling, I was reading about Daniel Leidar's work that was working with you guys on that and Rigetti. And can you speak a little bit to the other areas in which you guys are working at the abstraction layer to make advances in this space? Because I think it's one of the unique aspects of quantum computing versus other sort of chipset technologies that have come about in the past.
Yeah, so this morning we heard about software abstracting, and then at the moment I realized, well, I'm talking about going deeper. Because at this stage in time, being able to understand what goes on deeper is kind of a prerequisite. We try our best to abstract away everything, but we don't know all the tricks yet. So what I talked about today was you kind of need to know what's going on if you want to really optimize things. And so the reason this was my talk is because I could have showed you how to build a circuit, I could have showed you how to run it on a simulator and all these things, but this is kind of stuff that people know how to do already. It's not so complicated. But when you really want to take advantage of quantum systems in the noisy regime, right, at least at present, you really need to know what's going on when you compile the hardware, right? We are working to try to abstract that away. Again, we have a default set of passes that work pretty good, but one of the outstanding questions is, if a user gives me a random circuit that I've never seen before, I want to know a priori what passes to do. I don't want to have to do every pass on it because those are expensive, right? So which passes do I do if I'm given a random input circuit? That's something we need to answer. And it probably won't be a question where you get the optimal circuit, but I should be able to come up with heuristics that get me close. And in some sense, that's already what's being done when you say, I want to map to my hardware. Because mapping to hardware with respect to like swap mapping is an NP-hard problem. Okay, so it doesn't scale even if you can find the exact optimal. So you have to come up with heuristics. Okay, in our software, the heuristic is your swap mapper is now a stochastic algorithm. So your circuit actually changes if you run it repeatedly. And so the idea there is that the stochasticness gets around being NP-hard, but you may have to run it 2 or 3 times to find the shortest one. If you're talking about things in general, this is what we call aqua. Aqua tries to abstract away most of the stuff you would need to know to run, for example, the VQE we heard about earlier. You just need to do an input and it will do that. Finance, it'll do the same thing. If you give it a particular set of inputs to solve risk analysis, it will go build the circuits for you, run them on our hardware or simulators, return the result. So it depends on where you're asking about the abstraction. So there's the applications level, that's aqua. At the lower level, we have some work to do. But it keeps us employed. Right? So, yeah.
There's some software companies out there that are specializing in algorithms for error mitigation.
Mm-hmm.
Would we be able to use some of their software with OpenPulse?
I would assume maybe. If you don't have access to hardware, it's hard to be a company in error mitigation. Right? So, whether that's us or someone else, I can't tell you.